welcome back to the session on power electronics and instrumentation. In the previous session we were discussing about the different turn off methods. So, turn off methods or turning off of a thyristor, that process is also known as commutation as already discussed. Okay, so we have already seen the class A type of commutation. This classification as class A, class B, class C is based on the placement of the commutating components. So, in the previous class A commutation type of circuitry, we have seen that the commutating components, that is inductor and capacitor, was connected in series with the load resistance. So, now in the case of this circuit, we can see that the commutating components inductor and capacitor is placed in parallel with the thyristor. So, such an arrangement of the commutating components in a circuit is known as the class B commutation process. So, now let us see what is the actual working of these commutating circuits that is responsible for turning off of the thyristor. So, as we go in detail, now we know that since the voltage supply is a DC source, we know that once a DC, that is a thyristor, is connected with respect to the DC supply, constantly the thyristor will be in its on state, provided we have supplied the gate triggering. So, once the gate triggering is supplied and the thyristor is connected in a DC supply, always it will be constantly in its operating mode. Okay. So, now what happens is, we do not want the thyristor to be always in its on state, because we will be using this thyristor as a switch. Switch means it should turn on and turn off desired by the circuit designer. So, depending on what the circuit designer wishes, that is for what amount of time the thyristor should be on and off, will be decided by the circuit designer. So, depending on that, in order to turn off the thyristor, here we have connected inductor and capacitor in parallel with the thyristor, and the load resistance is connected as shown here. Okay, so, now let us see how the working of the thyristor goes. Initially, when the voltage Vs is given, okay, initially when we are giving the circuit here, so then what happens? This current, the voltage that is applied across this, can follow two paths. You can see here there are two branches. So, this branch, the current will flow once the thyristor is being activated by providing the gate pulse. Till then, till you provide the gate pulse, what is going to happen is, once you are connecting this voltage across the circuit, when you are applying the voltage across the circuit, at the instant where the thyristor is turned on or turned off, now let us assume initially after 30 degree only we are going to turn, or let us say after some 10 nanoseconds we are going to give the triggering pulses to the gate of the thyristor. Okay. So, within the time 10 nanoseconds what we are having, this thyristor is off. Off means this is an open circuit condition. So, what is going to happen? The voltage that is applied here is going to follow the path through L and C. Okay. So, now what is going to happen? The voltage, this is in the off state, this starts storing its charges. As we know, L and C are the energy storing devices. So, when this thyristor is in its off state, the path of the current flow will start through this. Okay. So, L, C, since it is a positive polarity that we are applying here, the energy storing will also take the same signs. Okay. So, plus and minus, in the inductor energy is being stored, and on the parallel plates of the capacitor also the charges are being accumulated, okay, before we are turning on the thyristor. Now, once you are giving the gate pulse to the thyristor goes to its on state. On state means what happens? This is nothing but a closed path. the switch is closed. So when the switch is closed, what happens? Now there will be two currents flowing here. One is the load current through the load, the other one is this current due to the commutating components. Okay. Now till the thyristor is on, and these values L and C will charge up to a value of Vs. That is, voltage is applied, say 5 volt battery is applied here. So till the voltage, the energy being stored will be equal to the applied voltage Vs, till then the inductor and the capacitor will be continued to be in its charge state. Once we are applying the gate triggering pulse here to this thyristor, now what happens? Here we will be having two currents. One current is through the load current and the other is also known as the commutating current. So two currents, one is the load current and the other one will be the commutating current. Okay. Now what happens? One current, IL current flows through the thyristor and the load. At this point we are going to get the output voltage only when we are going to connect it to this thyristor switch. Okay. Now at the instant when the thyristor is in the on state, okay, what happens here is the capacitor starts discharging. Once thyristor is on, capacitor starts discharging. Discharging of the capacitor means what will happen? Reversal of polarity will take place. So minus plus, minus plus. Here it is only Vs, positive Vs is applied at this point. At this point you can see it is being charged to plus Vs, minus Vs, minus Vs. So this voltage will be equal to minus 2 Vs. The potential of this is more. Okay. So it will be, this negative voltage is going to be influencing the thyristor in such a way that this thyristor is made to go to its off state, because at the anode we are going to apply the negative voltage. So the current, that is the path chosen by the current here, will be equal to, it will start from the positive plate of the capacitor. Let me say this is a positive and this is the negative plate. So positive plate of the capacitor, then it goes to the inductor. From the inductor it moves to the thyristor and comes back to the negative of the, or the lower plate of the capacitor. So this is the commutating path that is followed, that is going to put the thyristor in the off state. So this is how, by using the components L and C, forcefully we are going to turn off the thyristor. The respective waveforms are, only when you are applying the gate current you will be getting an output voltage across the load. Okay. So when you are applying the gate current you are getting the load current, but at some instant, that is before the next gate pulse only, by making use of this L and C commutating components, we are going to turn off the thyristor in between. Thyristor is off means we are not going to get any load current. So we don't know at what instant of time we are going to turn off the thyristor. So somewhere it is going to be in its off state before the application of the next gate pulse. Okay. So the next gate pulse is applied, again thyristor will be in its on state. When thyristor is in its on state, then what is going to happen? The load is being connected to the source and we will get an output voltage. So here what will happen? We are going to get an output load for the next instant of the application of the gate pulse. Similarly, IT is the current through the thyristor. We know that when the thyristor is in the on state, we are going to get a high value of current, but somewhere in between it is going to go to its off state depending on the values of L and C. Later we will see how we are going to choose the values of L and C in order to find out what is the time at which we can turn it off. So initially thyristor current, when we are getting the load current, thyristor current will be at its maximum value, maximum current will be flowing, suddenly it will go to the off state. Then next again when you apply the gate pulse, your thyristor is in the on state, then the current flows the current in the thyristor starts increasing. Similarly, coming to the voltage across the thyristor, we know that when the thyristor is in the on state voltage drop is around 0.7 or 0.8 volts. So, we are taking a straight line. Thyristor is on, current will be high, but the voltage applied is 0.7 or 0.8 volts. During the off state, we know that reverse recovery time plus the recombination time constitutes the off time. So, depending on that time interval, this can be approximately around nanoseconds. If we are using in the PN junction, that is in the thyristor, if we are going to use the silicon as the material, then the off time will be somewhere in nanoseconds, 10 nanoseconds to 100 nanoseconds or sometimes microseconds. Okay. So, this is how it is going to go to the off state. Okay. Once it is at some instant of time till T off, it is going to go to the off state. Then what will happen? Then whatever the input voltage was given, that will be displayed across thyristor. Again, when the gate pulse is applied here, what is going to happen? Thyristor is going to go to the on state, means the on state voltage drop is 0.7 or 0.8. So, you can see a straight line here. So, this is how we are going to turn off the thyristor by making use of a class B commutation circuit. Now, in order to find out what can be the values of L and C that we can choose in designing this thyristor or the commutating components, let us see the application of KVL here to this circuit in the commutating part. So, here when the circuit is closed, what happens here? Thyristor is in the on state. So, the voltage drop across the thyristor is around 0.6 or 0.7 or 0.8 volts. So, now what happens? This is 0.7. So, the current circulating here in this direction will be L into di by dt plus 1 by C into integration of I into dt. The voltage that we are getting is equal to 0. Fine. Differentiating this with respect to t in order to eliminate the integration, we are going to differentiate this homogeneous equation, differential equation. So, we are going to get a second order homogeneous differential equation. Now, this second order homogeneous differential equation, we know already the solution for second order homogeneous differential equation. Before that, what we have to do? Take the Laplace transform of it. So, d square will be converted into s square, L into I of s plus 1 by C into I of s. So, take the common I of s as common and write the equation. The solution, when we convert it into inverse Laplace transform, we are going to get it as I of t current flowing is equal to Vs into root of C by L. Okay, into sine omega naught t, where omega naught t is the natural frequency. That is, natural frequency means whenever you are going to use the L and C circuit together, it behaves as an oscillator circuit. So, we will get a natural frequency omega naught is equal to 1 by root of LC. Okay. So, how can you calculate the commutation current? Peak commutation current because of these commutating components is nothing but IC peak is equal to Vs into square root of C by L. And to determine the turn off time, T off is equal to pi by 2 into square root of LC. So, these are the expressions that are used for finding out the commutation current as well as to determine the off time from this class B commutation circuit. So, this completes the class A and class B type, that is the turn off methods of thyristors. Next, we will discuss few problems related to this module. Now, before starting to solve the problems, first we need to analyze the equation of current for the different load conditions. Now, if the load is a resistive load, then applying KVL here, how can we find out the current flowing here in this circuit? Apply KVL here, you will get Vs is equal to, when the thyristor is in the on state, it provides a closed path for the circuit. only then we can calculate the current flowing in the circuit. When it is off state, this link will be broken. It is an open circuit condition where we will not be able to find out what is the current flowing in the circuit. Okay. So, if it is for a pure resistive load, then we will write the equation as Vs is equal to I into R. Simple. Then to find out the current, what we are going to do? Vs by R is how we are going to find out the current flowing. Whether Vs is a AC source or a DC source, depending on that we are going to substitute and find out. Suppose if instead of writing only the R, if we are going to get in the problem, it is connected to a R and L load. Okay. In such a case, what happens? L is nothing but the energy storing device. So, the charge in energy will be stored and energy will be released in an inductor. So, we cannot directly make use of this concept. So, what we are going to do is, we are going to apply KVL here for this circuit. Now, let us see how the KVL application for this circuit goes. Let us say I is the current flowing in the circuit. So, R into I plus, since you have an inductor is related with respect to the current as di by dt. So, the voltage developed across the inductor is L into di by dt is equal to the voltage that we are going to apply. This is from applying KVL to the circuit. Okay. So, this is the KVL. Now, let us divide this equation by L. Okay. So, if you are going to divide, how will the equation look like? di by dt plus R by L into I is equal to Vs by L. Let us call this as equation number 1. Now, this equation represents the first order non-homogeneous differential equation. Okay. So, first order non-homogeneous differential equation means how it will be of the form, the general form you might have studied. Let me say dx by dt plus p into x is equal to q. So, the solution for this first order non-homogeneous differential equation can be written as x is equal to e to the power of pt into integration of q into e to the power of plus pt into dt plus the integration constant k1 into e to the power of minus pt. This is the generalized solution for a first order non-homogeneous. Why do you say a non-homogeneous differential equation? Because equal to some value is present. When the equation goes as equal to Vs by L, it represents a non-homogeneous. If it is equal to 0, if any of the equation will be equated to 0, it represents the homogeneous condition, whereas here it represents the non-homogeneous equation, differential equation. Since we have di by dt, it is a differential equation. So, for this equation, the resemblance of the generalized format is like this. So, the solution for the first order non-homogeneous differential equation, for this equation, here it was with respect to x, but here it is with respect to I. So, we can write the equation as I of t is equal to e to the power of, what is p here? Let us say this as p and this as q. Okay. So, now how will you get it? I of t is equal to e to the power of minus pt minus r by L into t plus integration of q. Q is nothing but a constant which is not a variable of t. So, directly you can write Vs by L is into e to the power of pt, e to the power of pt with respect to dt. So, e to the power of r by L into dt plus the integration constant K1 into e to the power of minus R by L t. So, this is the solution for the equation 1, which is of the type of non-homogeneous first order differential equation using this solution. Now, let us substitute here to find out the solution for it. We want the expression for I of t. So, I of t is equal to e to the power of minus R by L t. Vs by L is a constant, so take it outside the integration into integration of e to the power of plus R by L t, we should write t here, into dt plus K1 into e to the power of minus R by L into t. Now, integrating e to the power of at with respect to t, we get e to the power of at divided by t. That is the standard form. E to the power of at into dt integration will be equal to e to the power of at by a. Similarly, applying this integration principle here, we are going to get e to the power of minus R by L t into Vs by L into e to the power of R by L t divided by e to the power of at by a. So, R by L plus K1 into e to the power of minus R by L t. Okay. Now, what will happen? L and H can be cancelled. E to the power of minus at into e to the power of plus at will be equal to minus a plus a will be equal to 0. So, e to the power of 0 is 1. Okay. Let me write it clearly. E to the power of minus at into e to the power of plus at is equal to minus a into plus a will be to the power of 0, which is equal to 1. So, this term will be also eliminated here. So, what is the remaining now? Remaining is Vs by R plus K1 into the power of minus R by Lt. This is equal to I of t. Call it as equation number 2. Followed? Next, let us consider the initial condition. Let us say at the instant when you are applying the time at 0, what will happen to the current? Current also in the inductor will initially be 0 at the instant of time t is equal to 0. So, at time t is equal to 0, that is initial conditions, the current when the time is equal to 0 will also be equal to 0. So, using this principle here in equation 2, we will get it as current at time is 0 is 0, that is equal to Vs by R does not have any time constant, plus K1 into e to the power of 0 is again 1. So, K1. Now, you should find out the value of this integration constant K1. So, for finding out the integration constant K1, you can bring this K1 to the other side of the equation, we will get minus Vs by R. Call this as equation number 3. Substitute this equation 3 in equation 2. Equation 3 in equation 2. If you substitute, what will you get? I of t is equal to Vs divided by R minus, instead of K1 we are going to write Vs by R into e to the power of minus R by L t. Now, we can find out from this equation Vs by R is in common. So, what we can do? Take the Vs by R common outside. So, the equation will be I of t is equal to Vs by R into 1 minus e to the power of minus R by L into t. So, this is the equation for finding out the current in a RL circuit. So, while solving the problem, they will give us the value of R and L. You have to find out using this equation. Directly we have to use this equation. If and only if they ask you to derive the equation, then you should follow this step. Otherwise, directly the problem statement will be given. The value of Vs, R, L will be given. Find out the current or the time. Okay. So, you have to remember this equation. If it is only R load, this equation is sufficient, Vs by R. If it is an RL load, then you should remember this equation which goes like this. Now, let us see the first problem which states that the SCR shown in figure 1, let us say this is the figure 1, has the latching current of 20 milliampere. Okay. As you read the statement of the problem, write down the given specifications which says that, let us say the solution, latching current is 20 milliamperes and is fired by a pulse of width 50 microseconds. Pulse of width means, let us say T is 50 microseconds. This is a firing pulse. Determine whether the SCR triggers or not. Okay, the latching current is given. Latching current means it is the minimum current that is required for the thyristor to go to its on state. Only if this value, whatever is specified, okay, if that is given, only then you can find out what is the value of the latching current. Okay, the R and L values are given as 20 ohm and as 0.5 Henry, and the Vs supply voltage is given as 100 volt. Now, by seeing the circuit itself, you know it is a RL load circuit. So, we know that only when the thyristor is in the on state, we are going to get the load voltage. So, first find out the current. In order to find out with these specifications, will there be a current that will reach this latching current? Only if the current from this circuit reaches the latching current specified, only then SCR will be in its on state. Okay. So, as we have R and L, directly substitute this equation. I of t is equal to Vs by R is equal to 100 volt divided by R is 20, 1 minus e to the power of minus R value is 20. L is 0.5 into T is, what is the value of T? 50 microseconds. Okay, so R by L into T. So, when you solve for this, you will get the current approximately. You solve it and tell what is the value of current. Now, for this instant, as I have already solved, I am getting it as 10 milliamperes. Once you solve this equation. So, now we have to find out what happens here. 10 milliampere is the current we are getting for this specification with the pulse duration of 50 microseconds. 10 milliampere is the current we are getting. So, this current, what about the latching current? It is 20 milliampere. But what is that you have got? 10 milliampere. So, this current whatever you have got is less than 20 milliamperes. So, what will happen? Will the thyristor get turned on? No, it will not be turned on because the current that is generated for a pulse width of 50 microseconds is not sufficient for turning on the SCR. So, you have to write this. They have asked determine whether SCR triggers or not. So, you have to write a sentence telling that due to the current as 10 milliamperes compared with the latching current of 20 milliamperes, SCR does not get triggered. This is how you should write the solution for the problem. Few more problems we will continue in the next session. Thank you.